Right now, not in a movie, not in a simulation, 4 human beings are falling toward Earth at 40,000 kilometers per hour. The air in front of their capsule cannot move out of the way fast enough. It compresses, superheats, and transforms into plasma, a sheath of ionized gas so dense it swallows every radio frequency known to engineering. No signal reaches them. No command gets through. Houston's screens go dark, and here is the part that should keep you awake tonight. The only thing standing between those 4 people and temperatures that would vaporize exposed titanium in under 1 second is a layer of material a few centimeters thick. A material that on its last mission in November 2022 broke apart in over 100 locations in ways that no simulation had ever predicted. NASA saw the damage. They studied every photograph. They ran every model. And then they put people inside anyway. This is not a story about reckless courage. This is a story about what happens when the most sophisticated space agency in human history reaches the edge of what physics allows and has to make a decision with no good options. Subscribe if you want to understand why. Now, let's count down. To understand why Artemis II matters, you need to understand what humanity gave up and for how long. December 7, 1972. Eugene Cernan climbs back into the lunar module on the surface of the moon, seals the hatch behind him, and becomes the last human being to stand on another world. He is 40 years old. He expects to go back. Everyone expects to go back. Nobody goes back. For the next 54 years, every human being who leaves Earth stays within roughly 400 kilometers of the surface. The International Space Station, the Space Shuttle, SpaceX Dragon, every mission, every headline, every giant leap, all of it happening in a thin shell of space so close to Earth that astronauts can look down and identify city lights at night. That is not exploration. That is orbiting. The distance between low Earth orbit and the moon is roughly 380,000 kilometers. We have not crossed that distance with a human crew since 1972, not because we forgot how, not because we ran out of rockets, but because the problem of getting there was never the hard part. The hard part was always getting home. Orion, the capsule carrying the Artemis II crew, will travel over 46,000 kilometers from Earth. It will swing past the far side of the moon, reaching a point roughly 7,600 kilometers beyond it, farther than any human being has ever traveled in the entire history of our species. Every single meter of that record-breaking distance has to be paid back at re-entry, and the faster you go out, the faster you come back. 40,000 kilometers per hour, Mach 32, the fastest any human crew has ever re-entered Earth's atmosphere. This is not a return to the moon. Not yet. This is humanity proving it remembers how to survive the journey home. And that proof hinges on 4 minutes of radio silence and a heat shield that has already surprised the people who built it. Most people understand that re-entry is dangerous. Very few people understand why, at a physical level, it is so close to being impossible to survive. Let us walk through what is actually happening to the Orion capsule in those final minutes. When Orion hits the upper atmosphere, it is traveling at just over 40,000 kilometers per hour. That is Mach 32, 32 times the speed of sound. For context, a bullet fired from a standard military rifle travels at roughly Mach 3. The Orion capsule is moving more than 10 times faster than that. At those velocities, the air molecules in front of the capsule face a fundamental problem. They cannot move out of the way fast enough. The capsule is arriving faster than the pressure wave that would normally push air aside. So instead of parting, the air compresses violently into a shock wave directly in front of the heat shield. That compressed air does not simply get warm. It gets hot enough to strip electrons from individual atoms, crossing into a fourth state of matter that most people never encounter outside a physics textbook. That state is plasma. The temperature on the face of the heat shield climbs past 2,760 degrees Celsius. To put that number into physical terms your body can process, structural steel melts at approximately 1,370 degrees. Titanium, one of the strongest and most heat-resistant metals used in aerospace engineering, fails at around 1,670 degrees. The carbon fiber and titanium skeleton of the Orion crew module would become liquid in under 1 second without protection. But plasma does something beyond generating heat. It creates what engineers call a plasma blackout, a communications dead zone that has haunted human spaceflight since the Mercury program in the early 1960s. Plasma absorbs and reflects radio waves across virtually every usable frequency band. It does not weaken signals. It eliminates them entirely. You can think of it this way. Imagine wrapping the entire capsule in a shell of molten metal several meters thick. No signal enters. No signal exits. For approximately 4 minutes during peak heating, the crew of Artemis II is completely unreachable. You use your phone every day. You know the frustration of losing signal in a tunnel or an elevator. Now remove the tunnel, remove the elevator, replace them with a fireball traveling at Mach 32, and understand that the silence is not a technical inconvenience. It is a physical law. In Houston, flight director Rick Henling and his entire team will sit at their consoles during those 4 minutes watching screens that show nothing. No telemetry, no voice, no data of any kind. They have trained for this silence. They know it is coming. Knowing it is coming does not make it easier to sit through, because everyone in that room understands the same thing. So when the signal returns, they will have their answer instantly. And if it does not return, no explanation will be necessary. The capsule survives because of a material most people have never heard of, avcoat. It is not a metal. It is not a ceramic. It is not the kind of shield you picture when you imagine a spacecraft returning from deep space, rigid, reflective, impenetrable. Avcoat works on a principle that feels almost counterintuitive the first time you encounter it. It protects by destroying itself deliberately in a precisely controlled sequence that engineers have spent decades trying to understand, and that still, in certain conditions, manages to surprise them. Here is how it works. As the heat shield surface contacts the superheated plasma, the outermost layer of Avcoat chars. That charring process absorbs enormous quantities of thermal energy. I'm pulling heat away from the structure beneath. The charred material then erodes into the airstream, carrying the absorbed heat with it. A fresh layer is exposed. That layer chars, it erodes. Another layer is exposed. This continues for the entire duration of peak heating, layer by layer, the shield sacrificing itself in a controlled retreat so that the crew module behind it stays within survivable temperature limits. Think of a candle. A candle does not block heat. It absorbs it through the process of melting, converting solid wax into liquid and vapor, carrying thermal energy away in the phase transition. Avcoat does something structurally similar, but at 2,760 degrees Celsius and with a timing precision measured in milliseconds. NASA used Avcoat on every Apollo command module that returned astronauts from the moon between 1968 and 1972. It worked flawlessly every single time across 11 crewed missions. So when Orion needed a heat shield capable of handling lunar return velocities, the decision to return to Avcoat seemed straightforward. The manufacturing process, however, was not the same. The original Apollo heat shields were constructed as a single unified honeycomb structure containing roughly 320,000 tiny hexagonal cells. Each cell was filled by hand with Avcoat material, painstaking work that required months of careful labor, but produced a shield with near-perfect thermal uniformity across its entire surface. For Orion, Lockheed Martin modernized the process. Instead of filling hundreds of thousands of individual cells, engineers manufactured approximately 186 pre-machined Avcoat blocks, each designed to fit a specific position on the heat shield's 5-meter wide carbon fiber base. The blocks were bonded into place like pieces of a puzzle. It saved significant time and cost. Whether it preserved identical thermal performance was a question that ground testing could not fully answer. The only way to know was to fly it. And there is one more detail that rarely gets mentioned in coverage of this program. Many of the engineers who built the original Apollo heat shields by hand are no longer alive. The institutional knowledge embedded in that process, the small adjustments, the tacit expertise, the things that never made it into any manual, did not transfer completely to the next generation. In a meaningful sense, humanity is not simply returning to the moon with Artemis. We are relearning how to survive the journey home using tools we rebuilt from incomplete memory. November 16, 2022, an uncrewed Orion capsule splashes down in the Pacific Ocean after a 25-day journey around the moon. By nearly every public metric, Artemis I is a triumph. The rocket performed, the capsule performed. The mission achieved everything it set out to demonstrate. The celebration lasted until engineers got the capsule back to Kennedy Space Center and removed the heat shield for post-flight inspection. What they found was not catastrophic failure. It was something more unsettling than that. Unexpected behavior in a system that was supposed to be fully understood. Over 100 locations on the shield showed irregular char loss. Large sections of Avcoat had cracked and broken away in jagged, unpredictable chunks. not the smooth, controlled ablation that decades of ground testing had predicted, not the uniform layer-by-layer retreat that the Apollo missions had demonstrated across 11 flights. Something different had happened, and it correlated precisely with a single decision in the flight plan. Artemis I used a technique called skip reentry. Instead of diving directly into the atmosphere on a single continuous arc, the capsule first dipped into the upper atmosphere to shed velocity through aerodynamic drag. It then used its aerodynamic lift to skip back above the atmosphere, like a flat stone bouncing off the surface of a pond. After a brief coast in near vacuum conditions, it dipped back down for a final descent. The advantage is precision. Skip reentry extends the range of possible splashdown locations, giving mission planners significantly more flexibility. Apollo never had this capability. It was supposed to be the modern upgrade. Inside the AVCOAT, it triggered a chain reaction that nobody had modeled correctly. During the skip phase, when the capsule climbed back above the atmosphere, external heating dropped sharply and rapidly. That temperature drop triggered a process called pyrolysis. AVCOAT burns internally without oxygen, producing gases as a byproduct. Under sustained high heat, those gases vent outward through the porous char layer in a self-regulating system. But when heating paused during the skip, the char layer cooled, contracted, and became denser, less porous, less permeable. The AVCOAT underneath was still warm enough to keep producing gas. That gas had nowhere to go. Pressure built inside the blocks, quietly, invisibly. And when the capsule plunged back into the atmosphere for its second heating pass, those pressurized internal pockets ruptured, blowing charred material off the shield surface in irregular chunks that no simulation had anticipated. Here's the detail that makes this story genuinely difficult to process. Despite the damage at over 100 locations, the temperature inside the Orion cabin never exceeded the mid-20s Celsius. The AVCOAT was doing its primary job, blocking heat from reaching the crew module, even while tearing itself apart in ways that were completely unpredictable. An ablative heat shield with uncontrolled ablation is like a parachute that opens but may develop random holes at random locations during the descent. It will probably slow you down. You simply cannot calculate by how much. And that uncertainty, not the heat, not the damage itself, is what kept engineers awake after Artemis I. After Artemis I, NASA faced a decision with no clean answer. Replacing the heat shield entirely would have added years to a program that had already slipped from 2024 to 2025 to 2026 through a cascade of technical delays, hydrogen leaks, and weather disruptions. The shield was already bonded to the crew module. The crew module was already integrated into the stack. To be entirely fair to the engineers who argued for proceeding, the data from Artemis I, while unexpected, showed thermal performance within acceptable limits. Cabin temperature remained stable. No structural threat to the crew module was confirmed. That is a legitimate technical position supported by real numbers. But aerospace engineering does not operate on the principle of probably fine. Columbia did not fail because cabin temperature rose. It failed because a piece of foam struck a wing during launch and nobody caught it in time. 7 people, 1 undetected crack. NASA eliminated the skip re-entry entirely. Orion will fly a steeper, more direct descent, hitting the atmosphere harder for a shorter duration, with no pause in the middle where trapped gases can accumulate and fracture the shield from within. The trade-off is higher gravitational forces on the crew and greater structural loads on the vehicle. But the failure mode is one they now understand. That is the most honest summary of where the science stands, not a solved problem, but a better understood risk replacing an unpredictable one. Consider what it means to read a damage report about the object keeping you alive. All 4 members of the Artemis II crew reviewed the full Artemis I heat shield investigation. They saw the photographs of the irregular char loss. They studied the modified descent profile, the risk assessments, the updated thermal models. They understood the numbers. They understood what those numbers meant in physical terms, and then they got into the capsule anyway. Reed Wiseman spent years landing fighter jets on aircraft carrier decks at night, essentially parking a vehicle traveling at 250 kilometers per hour onto a moving platform the size of a tennis court in darkness over open ocean. He has a calibrated relationship with acceptable risk. Victor Glover flew combat missions and lived aboard the International Space Station. Christina Koch spent 328 consecutive days in orbit. Jeremy Hansen is a former fighter pilot and the only crew member who has never been to space before. These are not people who misunderstand danger. These are people who have spent careers developing precise, unsentimental relationships with it. Their decision to fly does not mean the risk is acceptable by any universal standard. It means they looked at the same data every engineer looked at and reached a conclusion that no equation can fully capture. Some destinations are worth the honest probability of not coming back. The plasma blackout is not a new problem. It has defined every human reentry since the Mercury program. And history has given us 3 moments that illuminate exactly what that silence means and what it can cost. April 17, 1970, Apollo 13. The service module has been crippled by an oxygen tank explosion 4 days earlier. Nobody knows whether the command module heat shield was damaged by the blast. The expected blackout is 3 minutes. It stretches past 4, then 5, then 6. Flight director Gene Kranz and his team sit in total silence watching a clock and a blank screen. When astronaut Charlie Duke finally hears Jack Swigert's voice cut through the static, the room breaks open. The signal came back. February 1st, 2003, Columbia, the expected blackout begins normally. The signal does not return. Mission control watches telemetry vanish and waits for a transmission that never comes. The crew received no warning. 7 people. A foam strike during launch that went undetected and unaddressed. Heat shield failure during re-entry is not a theoretical category of risk. It has a date. It has names attached to it. April 10th, 2026. Artemis II, the expected blackout is 4 minutes. Everything that comes after that silence, every lunar landing, every deep space mission, every piece of infrastructure humanity hopes to build beyond Earth depends on what the signal sounds like when it returns. If it returns, there is a second risk threaded through this mission that receives a fraction of the attention given to the heat shield. And in some ways, it is the more philosophically uncomfortable one, because it is a risk that cannot be fully quantified until it actually happens to someone. The Artemis II crew launched during the peak of solar cycle 25. Solar cycles run approximately 11 years from minimum to maximum activity. The years 2025 and 2026 represent the most volatile period of solar behaviour in roughly 2 decades, a window during which the sun is capable of ejecting massive streams of high-energy particles into the solar system with very little warning. Inside low Earth orbit, the crew would be protected by Earth's magnetic field, the Van Allen belts, a pair of invisible radiation shields generated by our planet's molten iron core. Think of them as a planetary immune system deflecting and trapping high-energy particles before they reach the surface. Beyond the Van Allen belts, that protection disappears entirely. Orion carries a dedicated radiation shelter, the most heavily shielded section of the capsule, where the crew can gather if a solar particle event is detected. It is designed to reduce exposure. Whether it is adequate under a worst-case solar event has never been tested with human beings aboard a spacecraft at this distance from Earth. That is not an accusation of negligence. That is simply the honest boundary of current human knowledge. No data exists because no human has been in that position during peak solar activity in the modern era of radiation monitoring. Artemis II is not just testing the heat shield, it is generating the first real data set on human radiation exposure beyond low Earth orbit in over 50 years. Data that every subsequent deep space mission will depend on. The crew knows this. It is, in a quiet and rarely discussed way, part of what they signed up for. What happens after the signal returns will determine the shape of human spaceflight for the next 30 years. If Artemis II succeeds, if the heat shield holds, if the modified re-entry profile performs as modeled, if the crew splashes down safely in the Pacific off the coast of San Diego, the path forward becomes measurable. Artemis III, the mission that will actually land astronauts on the lunar surface, moves from conditional planning to active preparation. The SpaceX Starship lunar lander, which will carry crew from Orion down to the surface and back, advances toward its first crewed demonstration. The Lunar Gateway, a proposed space station in lunar orbit intended to serve as a staging point for surface missions and eventually for deep space exploration, gains a foundation to build from. Beyond the moon, the data collected on this mission feeds directly into Mars architecture planning, radiation exposure profiles, re-entry thermal performance at velocities beyond low Earth orbit return speeds, human physiological response to deep space radiation environments. None of this exists in reliable form yet. Artemis II begins filling those gaps. But there is a question beneath all of this that 4 minutes of radio silence cannot answer. Humanity has now spent 54 years demonstrating that it can survive in low Earth orbit indefinitely. What we have not demonstrated is whether we can build the sustained institutional will, across administrations, across funding cycles, across generations to actually become a multi-world species rather than simply planning to become one. The engineering problems are difficult but finite. The political and cultural problems have no equation. Artemis II answers one question today. The larger question remains open. There is something worth sitting with about those 4 minutes of silence. The crew does not disappear during the blackout. They are still there, falling, breathing, trusting 50 years of accumulated human engineering to hold together around them. The universe is not watching. Plasma does not know it is surrounding people. Gravity does not adjust for significance. The physical laws operating on that capsule are identical to the ones operating on any rock falling through any atmosphere anywhere in the cosmos. The only thing that makes this moment different from a rock falling is that we built the capsule, we trained the crew, we designed the shield. We are sitting in Houston counting seconds. The universe does not care whether the signal comes back. We do. And perhaps that is the only definition of meaning that has ever actually mattered. Not significance granted by the cosmos, but significance created by the species paying attention. The signal will return or it will not. Either way, today, humanity tried again. And 54 years from now, whatever civilization exists will look back at this moment the same way we look back at 1972 as the line between before and after. We will know soon.